Okay, where was I? Now this question we'd already done. If it, without air resistance, kickball would reach a maximum height of 6 meters, land 38 meters away. With air resistance, the ball would travel. It would be less and less. So less than 38 horizontal, less than 6.7 vertically. Air drag reacts against the motion. Like if it's moving this way, air drag is always against the motion. So it's slowing it down in both directions. Okay. All right, let's check out 45. A body B is moving at a constant speed in a horizontal circular path around point P, which diagram shows the direction of the velocity and the direction of centripetal force. All right, centripetal force definitely got to be towards the center, so it's got to be one of these two. The velocity's got to be tangential, so it's probably 3. All right, that's the only one that makes any sense at all. And let's just make sure we got the direction right. It doesn't say if it's clockwise or counterclockwise, so it's got to be that one. No other answer that makes sense. Love those questions, free points. It's one of those ones that is as straightforward as it seems usually. Which combination of initial horizontal velocity and initial vertical velocity results in the greatest horizontal range for a projectile over level ground? All right, greatest range is always at 45 degree launch, as long as we are neglecting friction. You wouldn't be asked this question with or without friction. So it's greatest range is 45 degrees. That's just something you have to memorize for the Regents. So whatever one gives us 45 degrees, which would be either this one or this one. But this one's gonna go higher and farther because it's moving faster. All right, that's all there is to know. This one would travel the same rate moving forward, but because the initial speed vertical is not as much, it's not going to go as high. Remember, with projectile motion, the time of flight's all dependent on what the delta y is, right? The greater the max height, the longer it's going to be in the air for. All right. Now, I had to start pulling some questions from another Regent, so we double back here. There'll be some short answer questions at the end, but as shown in the diagram below, a student standing on the roof 50 meter high building kicks a stone horizontal 40 meters per second. How much time is required for a stone to reach level ground? So, delta y equals 1/2 ay t squared plus v naught y t. All right, so the time of flight of something launched in the air only depends on the y component of the motion. Accelerating down, it's moving horizontally at a constant speed. All right, so we're just going to use that. V naught is 0 because it's launched horizontally. T is going to be 2 delta y over ay, square root of that. So plug in the math here, 2 times 50 divided by 10. All right, and I'm not putting signs in here because I know they're going to cancel. I'm not using 9.8 just because we're going to get close enough to the right answer. Now, these are all using 9.8, so I can tell by the way the decimals are. So let's see what we get and then see if it would have made a difference using 9.8. So I got radical 10, which is 3.16. It's got to be that one. If you don't like that it's that, I could do square root of 2 times 50 times not divided by 9.8. And I'm going to get closer to, I'm going to get closer to the 1.9. Oh, my calculator battery just died. Huh, that's funny. I thought this thing was solar powered. Great. All right, well, we'll see if I need it again later. All right, so 4 identical projectiles are launched. The 3.919 did show up if you go back and look at it. 4 identical projectiles launched at the same vertical speed, but at various angles above the level of ground, which diagram represents the largest total horizontal displacement. Boom. It's from a different test, right? They're the same question, 45 degrees. All right, on to the short answer. 57 through 59, I'll have to do with this. 1.5 times 10 to the third kilogram car. It's driven at a constant speed of 12 meters per second. Counterclockwise on horizontal circular track having a radius of 50 meters is represented below. On the diagram in your answer book, draw an arrow to indicate the direction of the velocity of the car when it's at the position shown. So it's got to make sure you draw that tangential. All right, it's instantaneous velocity, which is what at velocity when it's at that position. That's instantaneous velocity. That's all that is. Now, I didn't put the answer book thing here. It's literally just this drawing printed in the answer book, and you literally just draw the arrow. You can do that in pencil on the Regents. Calculate the magnitude of centripetal acceleration of the car. A equals v squared over r. Oops, v squared over r, not v squared over 2. 2-point question, so you know it's going to be just an equation right off the reference table. Plugging and chugging. V squared over r. The m doesn't even come into play. They want you to try to use the m. That's the way they do things. They like giving you more than you need. And I don't have a calculator because my calculator died. I'm gonna grab one real quick. 12 squared is 144, but we gotta get the right number. All right, let's see. So I hate these calculators. The buttons always stick, but maybe that's just because I don't use it enough. Divide by 50, 2.9. 2.9 meters per second squared. 2.9, come on. Meters per second squared. Very good. Like that question, centripetal acceleration. Don't accidentally solve for the centripetal force. That's an R. I need some white out. All right, base your answers to questions 60 through 62 on the information below and on your knowledge of physics. You know how I always laugh at that one. Your knowledge of physics, that's dangerous. Anyway, football thrown at an angle of 30 degrees above the horizontal. The magnitude of the horizontal component of the ball's initial velocity is 13 meters per second. The magnitude of the vertical component is 7.5. On the axis in your answer book, draw a graph corresponding representing the relationship between the horizontal displacement of the football and the time the football is in the air. Now, we did this question on the previous worksheet. I should have put it on this one, but I'll do it again now. All right. So what you got to realize in projectile motion, the horizontal velocity is constant. Whatever it was launched at, that's the speed it moves forward with the whole time. So whatever that horizontal component is, at 13 meters per second, that's what it is the whole time. Now, the y component goes down on the way up, 0 at the peak, and it gets bigger on the way down, and it's symmetric. It turns out, Vx is constant, right? Vy is subject to AY of negative 9.8 meters per second squared. So this has to be a linear graph. Displacement versus time. Don't put an arrow on that line. Do not put an arrow. Just make a nice linear line. That is put on the answer booklet. That you can do that in pencil. It's just a straight line. All right, horizontal displacement. Football's cut at the same height. Calculate the total time the football was in the air. All right. Delta y, El Grande here, equals 1/2 AY t squared plus V initial YT. Now, on your reference table, right, this is the way I always write it. I always like putting this term first, because it's a quadratic, okay? We never put the C constant first, or BX plus, we always write the quadratic. I don't know why Regents reference table writes it like this. So keep in mind, it's the same formula. D equals V initial T plus 1/2 AT squared. That's the same formula, all right? V initial YT, we're solving for T. The beauty here is, since we start and end at the same height, it goes up, comes down. Delta Y is, in fact, 0, all right? Delta Y is 0, so that's 0 equals 1/2 of negative, and we can use 9.8. We'll use 9.8. You can use 10 as well. T squared plus initial vertical velocity is 7.5 meters per second t. Now the signs here are very important, right? It's launched up, but the acceleration is down. So this is a case where you have to put the right signs on your acceleration and your initial velocity. All right. In the end, you would end up with a negative sign under the radical, which hopefully you would realize was wrong. Now I put the units in here once, right? I don't need to keep them throughout the equation. So I'm going to move this over there. It's going to become positive 4.9 t squared equals 7.5 t. One of the t's cancels. So then t equals 7.5 over 4.9. I'm running out of room. All right, 7.5 divided by 4.9 equals 1.5 seconds. All right, 1.53, 1.5 is fine. Don't need to go farther than that. All right, I had to go to another. These short answers are mixed from two different Regencies, both 2015 and 2016. So this one's kind of a good one, though. We haven't had anything about gravitation yet, right? Like actually using that gravitational force equation, gm1m2 over r squared. We could have used it back here on this question, but that would have been probably a bit too much. So here we go. Pluto orbits the sun at an average distance of 5.9 times 10 to the 12th meters. All right, Pluto's diameter is 2.3 times 10 to the 6 meters, and its mass is 1.31 times 10 to the 22nd. I don't know how you say that. Probably Charon orbits Pluto, moon of Pluto. Pluto's got like 2 or 3 moons, kind of crazy. With their centers separated by distance. So this means Chiron, I don't know. Has a diameter of 1.2 times 10 to the 6 meters and a mass of that. Okay, calculate the magnitude of gravitational attraction Pluto exerts on Charon. All right, there's Pluto, there's Chiron, whatever, it doesn't matter. Let's make a drawing here. The radius between them is, it's not between that, it's between this and this. So the reading is hard in this one. All right, you got to use the second sentence here. Okay, that's your radius for this first part, 1.96 times 10 to the 7th meters. All right, so Fg equals big G m1 m2 over r squared. All right, big G, I get that from the front of my reference table, 6.67. And please just double check these when you plug them in, even if you think you have it memorized. Because, there's so many constants at this point between big G, K, mass of a proton. And that can be confusing because look at 1.67, 6.67, 9.11, 10 to the negative 11. Things get confused. So don't try to be too clever. I haven't left myself enough room here. Oh well. So I need the mass of Pluto and the mass of Charon, which are in 2 different paragraphs there. So let's put the 1.55 times 10 to the 21 kilograms. And then this is not enough room, so I'm going to do something that is really ugly. I'm going to put it down here. Pluto's mass is 1.31 times 10 to the 22nd kilograms. And that's all over the distance between them squared, which is 1.96 times 10 to the 7th meters. And that whole thing's squared. Really annoying, lots of writing. I'm not going to like putting this into this calculator, but oh well, here we are. It's got the double E button, so that makes our life a little easier. I wonder if the AP Physics 1 students know how to use that button. All right. I don't know if we'll tell them if they don't. I'll give you guys an advantage. All right, and then on the bottom, you got to put everything in parentheses. Now, I'm being careful putting this in because this calculator I'm using doesn't show me the whole formula. I'm going to hit equals, and we're going to see here Fg equals 3.5 times 10 to the 18th newtons, hopefully. I'll go back and check the key at some point and issue a correction if not. All right, calculate the magnitude of the acceleration of Charon towards Pluto. Ooh, that is not nicely worded, right? When you think towards an acceleration towards an object, you'd think they're moving closer together, but they're not. Here's Pluto. They're in an orbit, right? So the centripetal acceleration is towards Pluto, right? But it's not moving closer because it's moving tangentially. So it's a centripetal acceleration, v squared over r. Now, wait a minute. We got a problem, right? Because we don't know the v. Okay, so check this out, though. We do know F net C has to be equal to mass times AC. F net C would be the gravitational force. So, ooh, this is a nasty question. I don't remember this one. All right, so A equals 3.5 times 10 to the 18th newtons divided by the mass of the planet. So we got to put the mass of Chiron back under here. 1.55 times 10 to the 21 kilograms. Man, that's a lot of stuff to keep track of this one, on that one. Not particularly hard, but, you know, that was a good example of, okay, I want to use that equation, but I don't have the right information. So then I got to kind of readjust and figure out which one to use. Very, very interesting. All right, 3.5 double E 8 divided by 1.55 double E 21 equals, again, it depends on whether or not I've done that first thing right in the calculator. Again, you could leave it newtons per kilogram. That's fine, but that's a meter per second squared. That does not seem... Oh, no, I guess that would be right, because... Oh, no. I didn't put the right... I did to the 8th. Ugh. All right, 3.5 double E... That double E button sticky. 18 divided by 1.55 double E 21. It's gonna, oh man, see, it didn't go. It's gonna be a little bit smaller. Cross that out. We've got 0.0023, so 1, 2, 3. You can leave it like that. It'd be 2.3 times 10 to the negative third. Like, I should have realized that because it's off by a factor of 10. State the reason why the magnitude of the sun's gravitational force on Pluto is greater than the magnitude of the sun's gravitational force on Chiron. Pluto's mass is more. That's literally all you need to say. You don't need to try to give me any fancy explanation. I'll give you a little bit further explanation. G m1 m2 over r squared, right? Essentially, the moon and Pluto, Chiron, or however you say it, I'm going to look it up after this video, and Pluto are the same distance away from the sun, right, on a solar system scale. So R is the same for both. So whatever one has the bigger mass is going to have more force on it. M1, you'll say, is the sun for each of them. M2 is the mass of each thing. And the mass of Pluto is bigger than the mass of its moon. All right? So, not a very pretty question. That took a lot longer than I wanted to, but there you are.